Hello everyone, how are you all? This is your ma'am Akshita and I'd like to welcome you all to this session today. We have finally reached towards the end of the chapters with respect to class 11 and in this particular case we shall be learning about hydrocarbons. Now what exactly are hydrocarbons? As the term itself suggests, hydrocarbons, that is compounds that are made up of hydrogen and carbon. Now, with respect to hydrocarbons, one thing that you need to understand is it is these hydrocarbons which further undergo various kind of reactions to give us various other organic compounds. You must have heard of haloalkanes, you must have heard of haloarenes, you must have heard of you must have heard of phenol, alcohol, aldehyde, ketone. All of these compounds are actually formed from hydrocarbons. So let's now try to understand hydrocarbons and how are we going to learn about it. But before we get there, I want you all to know that we shall be trying to cover this chapter in 3 parts. We shall be trying to cover this chapter in 3 parts. What are these 3 parts? Basically, we shall understand that hydrocarbons are categorized into 2 major categories. One is aliphatic, the other is aromatic. Under aliphatic, there is the demarcation of saturated and unsaturated hydrocarbons. Now, under saturated, we have alkenes. Under saturated, we have alkanes. Under unsaturated, we have alkenes. Alkenes. Please focus. And then alkynes. Please focus on the last 2 letters. Last 4 letters in the case of alkynes. Last 4 letters in the case of alkenes. And last 4 letters in the case of alkanes. Right? And aromatic, under this, we have benzene. Now, how are we going to learn about this? How are we going to learn about it? So, we will first try to understand alkanes in part 1. This is going to be part 1 of our lecture, which is the lecture that you guys are seeing today, this particular lecture. Then part 2 is going to be with respect to, alkenes and alkynes. And finally, benzene, where we will have part 3. Part 3. So let's start off. What exactly are we going to learn with respect to alkanes? So we are, of course, going to have the introduction. What exactly are alkanes? Okay, introduction of alkanes. After that, we will be learning about their methods of preparation. And after this, we will be learning about their physical, followed by their chemical properties. So this is what our session today is going to be comprised of. Now let's start off with the hydrocarbons. They are compounds of carbon and hydrogen, as I've already told, which is there in the name itself, hydrocarbons, compounds of hydrogen and carbon. And they are again grouped into 2 major categories, aliphatic and aromatic. Now what are aliphatic compounds? Compounds that do not have aromaticity, okay? And they are open chain compounds. And these aliphatic compounds are again categorized into 2 major categories, which is saturated and unsaturated. Under saturated, what you see is alkanes, and under unsaturated, what you see is alkenes and alkynes. Now, when you look at aromatic is they have aromaticity. Okay, they have aromaticity, and we have benzene as an example for this. As I've told, our session today is going to be comprised of with alkanes. So let's focus on alkanes. Now, the general formula of alkanes is CnH2n plus 2, where N is nothing but the number of carbon atoms. Okay, and you are well aware why alkanes are called. Why alkanes are called saturated. The reason is very simple. they are saturated with respect to hydrogen. They are saturated with respect to hydrogen. That is, for a given number of carbon atoms, alkanes tend to have the maximum number of hydrogen atoms, followed by alkenes and then alkynes. And this is by the virtue of their single bond between the carbon atoms. All right, so they are saturated for this particular reason, and all HCH bonds in alkanes are 109 degrees 5 minutes. 109 degrees 5 minutes. And what about isomerisms? They show chain isomerism. They show chain isomerism. And methane, ethane, and propane do not exhibit any kind of structural isomerism. This is important. And isomerism is exhibited by alkanes, which contains minimum of 4 carbons. That is, for alkanes to exhibit isomerism. For alkanes to exhibit isomerism, it is very important that they have a minimum. Of 4 carbon atoms. Now, alkanes. C4H10 butane has 2 isomers. N-butane, which is CH3, CH2, CH2, and CH3. N-butane, a straight chain. And the second one is isobutane. So you see the isomer, the structural isomer over here, the structural isomer here. These are the examples of chain isomers. Now, moving on. So this is with respect to isomerism. I hope what you know isomerism is. Now, preparation of alkanes. Now, it is very important. We are learning about hydrocarbons. We are learning about alkanes, but we need to know how to prepare them, right? We need to know how we can get them. And one way is from unsaturated hydrocarbons. Unsaturated hydrocarbons. As I already told you that hydrocarbons, that is your alkanes, you're well aware that alkanes are saturated. They are saturated. That is, for a given number of carbon atom, they have the maximum number of hydrogen atoms. Now, when we talk about the number of hydrogen atoms, now you need to understand that both alkenes and alkynes, upon hydrogenation, which is nothing but reduction, because hydrogen is being added, can give rise to alkanes. They can give rise to alkanes. They can give rise to alkanes. Okay, they can give rise to alkane. Now, what are the the ways in which you can get hydrogenated alkenes and alkynes? That is when you treat nickel with hydrogen, platinum with hydrogen, palladium with hydrogen, you will get alkanes, and that is what is written over here. Other catalysts used other than nickel are platinum, palladium, okay, platinum oxide for alkanes, okay, to form alkanes. Now, what you need to understand is nickel is generally more, I would say, feasible or more widely used because platinum is expensive. Okay, platinum and palladium is expensive in comparison to nickel. Platinum and palladium can catalyze the reaction at room temperature, but for nickel, it requires very high temperature and pressure. So for nickel to be able to form alkanes from the given alkenes or alkynes, it is important that high temperature and pressure is provided. Whereas platinum and palladium, they can give the reaction at room temperature. Another method is from alkyl halides. Now, what you have to do is, you see alkyl halides, when you talk about alkyl halides, beta, yeah. So when you talk about alkyl halides, okay, what are alkyl halides? That is to an alkyl group, a halide is added. Okay, now what we need to do is this halide that you see, this needs to be replaced. By hydrogen. In order to get your alkanes, and that is exactly what happens over here in the presence of zinc plus HCl. When zinc along with HCl interacts with alkyl halide, what you get is alkane plus hydrogen chloride. I would like to write it over here, that is C2H6 plus HCl. What you will get is this, C2H6 plus HCl, C2H6 plus HCl. Okay. Now, keynote, lithium aluminium halide can reduce only primary and secondary alkyl halides, but, sorry. So this is about how we get alkyl halides. We get this is how we get alkanes from alkyl halides. Now when you talk about LiAlH4, it can reduce only primary and secondary alkyl halides. It is capable of reducing only primary and secondary alkyl halides. But for tertiary alkyl halides, it gives elimination product. Now what is elimination? Don't worry, you will learn about elimination when we learn about alkenes, okay, when we learn about alkenes as beta elimination, but in detail you'll learn about this in second year, so don't worry about it. And NaBH4 reduces secondary and tertiary alkyl halides only. Okay, triphenyltin hydride PH SNH can reduce primary, secondary and tertiary alkyl halides. It can reduce primary, secondary and tertiary alkyl halides, as you can see on the board, Another method that is required, or another method that can be used to generate alkanes, that can be used to generate alkanes from using red phosphorus and hydrogen iodide is. So using red phosphorus and hydrogen iodide, we can get alkanes. For example, you're taking Rx, okay? Then you're taking RCH2OH, okay? RCH2OH, you're taking alcohol, you're taking RCH2OH, okay? You're taking RCH2OH, you're taking C double bond OH, you're taking RC double bond OH, you're taking RC double bond OH, and you're taking RC double bond OR. Now to all of this, you're adding red phosphorus in the presence of HI. What will you get? You will get RH over here, you will get RCH3, RCH2. No, it's not RCH2, it's going to be RCH3. Sorry. RCH3, RCH2. All of these, as you can see, is reduction because hydrogen is being added. This is one way. Another way is by Wood's reaction. Where dry ether is used, and this method, Wood's reaction, you cannot prepare, by using this method, you cannot prepare methane. Methane cannot be gotten from this method because as you see, there are two alkyl halides and this Na reacts with this X and removes it as X, and you end up getting R, single bond R. Okay, how does this happen? For you to understand this, you can learn it this way. R X plus 2Na plus XR in the presence of dry ether. Dry ether is going to give us nothing but, it is going to give us nothing but R, single bond R plus 2NaX. Plus 2NaX, as you can see on the board. Okay, so this method is used in the preparation of alkanes containing even number of carbons. It gives us, okay, this method is used in the preparation of alkanes containing even number of carbons. Methane obviously cannot be prepared by this method, and tertiary alkyl halides cannot be converted into alkanes by this method because they convert into alkenes due to elimination. For you to understand this, you need to understand that for Wood's reaction, they follow free radical mechanism. It follows free radical mechanism. That is a free radical is formed. That is a free radical is formed. That is a free radical is formed. Okay. And how does that take place? How does that take place? So for free radical to take place, it is important that this free radical mechanism takes place in three steps, beta. Takes place in three steps. Okay, the first step is homolytic fission. Homolytic fission. As they have taken CH3I as an example, I shall take that as well. Okay, so it is nothing but CH3I. Okay, in the presence of homolytic fission, where homolytic fission is taking place in the presence of ether, dry ether, you're getting CH3 free radical plus I free radical. Okay, iodine free radical, iodide free radical. Now, after this, coupling reaction takes place. After this, what takes place, beta? Coupling reaction takes place after this. Coupling reaction takes place after this, where the free methyl radical and another free methyl radical come together to give rise to ethane, okay, to give rise to ethane. Now what you need to understand is that homolytic fission and coupling reaction is what takes place. Homolytic fission and coupling reaction is what takes place. But in the case of tertiary alkyl halides, another secondary and tertiary alkyl halides, another mechanism or another step takes place, which is disproportionation reaction. This is seen in the case of secondary and tertiary alkyl halides. Secondary and tertiary alkyl halides. Let's take the example of okay, a secondary alkyl halide. Let's take the example of secondary alkyl halide. Let's take CH3. CH2. Let's take a primary alkyl halide only. Or should I take a secondary alkyl halide? Let's take a primary alkyl halide only, CH2I. This undergoes homolytic fission. You will get CH3, CH2 plus I. Now what happens in disproportionation reaction is, please clearly have a look. Now over here what happens is, beta, you take two free radicals of this side by side. Now technically this free radical is supposed to combine with this free radical, but instead what happens is there is a cleavage over here giving rise to one hydrogen free radical and one CH2 free radical. Now what happens is this hydrogen travels over here and this free radical travels over here, and as a result what you see is CH2 double bond CH2 plus CH3 CH3. Okay, now what you need to keep in mind is over here, that for primary and secondary alkyl halides, coupling products are the major products, whereas disproportionation product is, I'll not say major product, I'll say the primary product. What's the primary product? Is the secondary product for disproportionation. Okay, beta? Secondary product. Okay. Whereas in the case of tertiary alkyl halides, primary product is disproportionation product. Secondary product is coupling product. So now, based on all of this explanation, this particular line will make sense that tertiary alkyl halides cannot be converted into alkanes by this method. Okay, because they give rise to, disproportionation product. They give rise to disproportionation product. Now, this is about Wood's reaction, beta. This is about Wood's reaction. Let's now try to understand decarboxylation. Decarboxylation. You see over here for decarboxylation, what is taken? Okay, you see sodium salt of carboxylate, like carboxylic acid. Sodium salt of a carboxylic acid is taken along with NaOH to give rise to alkane. How are we getting this? Beta? What you need to understand is, when RCOOH is treated with Na, what you get is RCOONA, sodium alkanate. And this NaOH plus CaO, is called soda lime. It is called soda lime because we need dry NaOH. So the CaO is a dehydrating agent, okay? It is dehydrating agent because NaOH is hygroscopic. It tends to absorb water from the atmosphere. So the CaO that is there, it keeps it dehydrated. So the soda lime, when it is treated with sodium alkanate, you get RH plus Na2CO3, okay? RH plus Na2CO3. Now the same sodium alkanate is used in Kolbe's electrolytic method, and we get alkanes with even number of carbon atoms from this. Even number of carbon atoms from this. How does this happen? Let's take this example of RCOONA. This way you can remember it, beta. RCOONA in the presence of water. Two molecules of everything. Okay, two molecules of everything. Now, what basically happens over here is, please have a look. Upon electrolysis, this is how elimination is taking place. I'll not say elimination, breaking of bonds, I would rather say. And you will end up getting R, single bond R, plus CO2 plus NaOH plus H2, where R, that is your alkane and carbon dioxide, you will receive it at your anode, and NaOH and hydrogen gas at cathode. Two gases are liberated in this process, carbon dioxide and hydrogen. Two gases are liberated in this process, that is your carbon dioxide and hydrogen. And what you need to keep in mind is, you have to balance this equation, beta. So 2 moles of carbon dioxide, 2 moles of NaOH. Hydrogen 1 mole. You can take the example of CH3 COONA, CH3 COONA. This is treated with water. Upon electrolysis, this is how the bond is breaking. You will end up getting CH3 plus CO2 2 moles. That's 2 moles of NaOH plus hydrogen. I hope this is clear. Using this method, you can also prepare your alkenes as well as alkynes, and we will look at it when we get there. We will look at it when we get there in the next part. Now, finally, reduction. This is what I've already explained to you, that when red phosphorus in the presence of Hi, reacts with alcohol, reacts with aldehyde, reacts with carboxylic acid, it gives rise to alkanes. It gives rise to alkanes. So these are the various methods of preparation, but there is another preparation, that is Corey House synthesis. Corey House synthesis. Now in Corey House synthesis, we use Gilman's reagent beta. We use Gilman's reagent. This is R2CuLi. This is Gilman's reagent. This is Gilman's reagent. And using this method, we can prepare symmetrical alkanes. See, the problem was in Wood's reaction. What happened was, Wood's reaction, we could prepare symmetrical alkanes, and we could even extract symmetrical alkanes. We could separate them. But with respect to unsymmetrical alkanes, we could not separate them because the boiling points were so low. Right. So in Corey House synthesis, using Gilman's reagent, we are able to synthesize, at the same time extract both. With Corey House synthesis, we are able to extract as well as synthesize both symmetrical and unsymmetrical alkanes. So you see R2CuLi with Rx gives rise to RR plus RCu, where R dash is unsymmetrical. That is R. Let's say if R is CH3, then R dash can be any group other than CH3. It can be C2H5. Okay. So the alkyl group of dialkyl lithium cuprate may be methyl, primary, secondary, or tertiary. Now, what are the properties? What are the physical properties? See, properties are of two types, physical as well as chemical. So, let's now try to see the physical properties. Molecules possess only weak van der Waals forces of attraction, and as molecular weight increases, forces of attraction increases. Thereby, C1 to C4 are gases, C5 to C70 are liquids, and above C17 they are all solids. Talking about the boiling point, in case of alkanes, boiling point increases with increase in the molecular weight. Okay, due to increase in the van der Waals forces. Okay, as the molecular weight increases, the boiling point increases. As the molecular weight increases, the boiling point also increases. In case of chain isomers, the isomer with more branches has a low boiling point. So what you need to know over here is that boiling point is directly proportional to molecular mass, and for chain isomers, boiling point is inversely proportional to branches. That is, more are the number of branches, lesser will be the boiling point. Now, among isomers of pentane, the order of boiling point is pentane, isopentane, and neopentane, because pentane is, this is pentane followed by isopentane. isopentane, and then we have neopentane. More are the branches, beta, less is going to be the boiling point. Now, when we talk about melting point, alkanes with even number of carbon atoms have more melting point than odd numbers. You can say that melting point is directly proportional to symmetry. More is symmetry, more will be the melting point. That is why even number of carbon atoms have more melting point than odd number of carbon atoms. Okay, so succeeding odd carbon alkanes, because alkanes with even number of carbon atoms pack closely, which permits greater intermolecular attractions, attractions. Now, solubility. See, the thing is, we talk about solubility, they are hydrophobic in nature, beta. When you talk about solubility in water, see, for anything to be soluble in water, hydrogen bond needs to be there, no? But then, when you look at alkanes, there's really nothing. It can, bond with hydrogen to form a hydrogen bond. So, alkanes are lighter than water. These are insoluble in water and are hydrophobic in nature, but these are soluble in organic solvents, and their solubility decreases with increase in their molecular weight, because more is the molecular weight, that means bigger is the molecule, it will because it's big in size, it is very difficult for it to get into the interstitial spaces, okay, intermolecular spaces of the solvent and then get dissolved in it, because they are huge molecules, right? So, chemical properties. Now, with respect to chemical properties, beta, alkanes are, you can say, relatively more stable and inert in comparison to the other hydrocarbons. As a result, their chemical reactions, if you see, with respect to the others are less extensive. And these are interactive towards acids, bases, oxidizing and reducing agents. Under suitable conditions, alkanes undergo substitution reactions also. Under suitable conditions, they undergo substitution reactions as well. So, let's now talk about their chemical properties, talking about combustion. What is combustion? Combustion is nothing but when a compound in the presence of excess of oxygen burns, okay, burns to give rise to product, energy to give rise to product, energy and flame, right? So, they do undergo combustion to give rise to carbon dioxide, water and energy. Okay, so you can see methane undergoes complete combustion to give rise to carbon dioxide and water along with energy. Controlled oxidation. Now, the thing is, beta, controlled oxidation is a mixture of methane and oxygen when passed over heated molybdenum oxide gets oxidized to methanol. Okay, basically what they are saying is in controlled oxidation, depending upon the catalyst that you're using, you're getting a different product. Like you see over here, methane in the presence of copper at 523 Kelvin, 100 atmosphere is giving us what? It is giving us alcohol, that is methanol. Whereas the same methane is reacting with molybdenum oxide in the presence of 543 Kelvin and 100 atmospheres to give rise to methanol. So, you see, it's controlled with the help of the catalyst that you're using, the different catalyst, different product. So, thereby controlled oxidation. Ethane will oxidize in presence of manganese acetate, will give rise to acetic acid, or I would rather say ethanoic acid. This is nothing but controlled oxidation. That is, in the presence of a catalyst, the product formed is different for the same carbon compound, like as you can see in the case of methane and methane over here. Now, normal alkanes are resistant to the attack of oxidizing agents, but tertiary alkanes are, however, when attacked with KMNO4, which is a very strong, very strong oxidizing agent, beta, very strong oxidizing agent. Okay, it is a very strong oxidizing agent because the oxidation state of manganese over here is +7. So, it is only capable of undergoing reduction. Okay, it is only capable of undergoing reduction. As a result, it is a very strong oxidizing agent because it has the highest oxidation state. It is in its highest oxidation state. So they are oxidized to, corresponding alcohols. So you can see over here, this is giving rise to alcohol over here. Please have a look. I hope this is clear. Let's now talk about isomerization. As you can get from the term isomerization, that is over here, isomer is formed, beta. Isomer is formed. You see 1, 2, 3, 4, 5 carbon atoms. Okay, and you see the isomer over here. They are capable of undergoing isomerization in the presence of AlCl3 HCl, in the presence of AlCl3 and HCl. Aromatization, one second. There's one thing that's not required. Sorry. There's one thing that's not required over here, which is this. Yep. They're undergoing isomerization. Beta. Now, when you talk about aromatization, aromatization is nothing but formation of aromatic compound. So you see over here, this particular alkane is giving me benzene in the presence of Cr2O3 at 773 Kelvin at 10 to 20 atmospheres. Okay. Finally, reaction with steam. Methane reacts with steam to give rise to carbon monoxide plus hydrogen gas. Then we have pyrolysis, that is decomposition of higher alkanes into smaller fragments on strong heating in the absence of air, that is nothing but absence of oxygen, is called pyrolysis or cracking. Pyrolysis is a free radical reaction. You see C6H14 is giving rise to C6H12, C4H8, C2H6. So this is nothing but pyrolysis. Now, as you can see over here, lower hydrocarbon exist in gaseous state while higher hydrocarbons exist in liquid and solid state. Now, before we move towards conformational isomerism, I want to let you know about free radical substitution reaction. So as you know that they are capable of undergoing free radical substitution, you know that free radical is formed over here. Now, how does this take place, beta? When CH4 is treated with chlorine and when CH4 is in excess, in the presence of sunlight, you will get CH3Cl plus HCl. But when CH4 is treated with chlorine and when chlorine is in excess, in the presence of H nu, you will get carbon tetrachloride plus HCl. Carbon tetrachloride plus HCl. Okay, the reaction of fluorine is greater than, chlorine is greater than, bromine is greater than iodine. Okay, so the reaction of the reactivity of fluorine is much greater than chlorine, is greater than bromine, is greater than iodine over here. That is, iodine is the least. Now, when I talk about the mechanism consists of 3 steps, beta. Initiation, propagation and termination. Initiation, propagation and termination. Okay, the mechanism has 3 steps. It has 3 steps. Mechanism has 3 steps. Initiation, that is over here in initiation, over here free radicals are formed. Free radical of chlorine is formed, okay, in the presence of H nu to give rise to Cl. This is your initiation. Then is your second step, which is propagation. Propagation, that is nothing but CH3H. Okay. This will give rise to CH3 free radical plus HCl. This is your propagation. And this free radical will then interact. Another chlorine molecule and give rise to CH3 Cl plus Cl free radical. So you see, one free radical is generating another free radical, which is again generating another free radical and is forming product. So this is nothing but a cascade reaction, a chain reaction. Now, ma'am, can we terminate this? Yes, we can terminate this. We can terminate this. How can we terminate this? How can we terminate this? How can we terminate this? So the termination reaction is the third step, where the free radicals of chlorine will combine with that of chlorine to give rise to Cl2. The free radical of hydrogen will react with chlorine to give rise to HCl. The free radical of CH3 will combine with Cl to give rise to CH3Cl. Okay, and then the free radical of CH3 will combine with CH3 to give rise to CH3. Okay, beta. And as you are already aware, that tertiary is going to be more stable. Tertiary is going to be more reactive, I would rather say, towards secondary. Is going to be more reactive than primary, than methane, because hyperconjugation. Because of hyperconjugation, the free radicals formed for tertiary is going to be tertiary free radical, secondary free radical, primary free radical, and methyl free radical. More are the alpha carbons, more are the alpha hydrogens, thereby more is the hyperconjugation, thereby more reactive towards the reaction. This is with respect to substitution reaction, beta, substitution reaction. Let's now try to understand conformational isomerism. The rotation about carbon-carbon single bond is not completely free. The rotation is not completely free. There is a bound. Why? Because there is a bond there. It cannot happily rotate in the universe. No, there is a bond that is present, as a result of which it is not completely free, but it is not restricted as well. Okay. So the conformations of ethane are, the conformations in which hydrogen atoms attached to two carbons are far apart from each other are called staggered conformation. They are called staggered conformation, and the staggered conformation is said to be the most stable. It is said to be the most stable because the potential energy is the lowest over here. And the conformation in which hydrogen atoms attached to the two carbon atoms are as close as possible, they are known as eclipsed conformation, and this is the least stable because the potential energy in this case is the maximum. Okay, so in all conformations, the bond angles and the bond length remain the same. Of course, the bond angle and the bond length will not change, beta. So rotation about the CC bond in ethane is possible because of cylindrical symmetry of sigma bond between CC bond. So there is a projection, Newman's projections. Okay, the molecule is viewed at the CC bond head on. The staggered and the eclipse conformations are interconvertible by the rotation of one carbon with respect to the other and the sigma bond that is connected with them. So this is nothing but Newman's projections, and look at this. This is the front carbon. This is the front carbon, this is the back carbon. Now look over here. Now the hydrogens are so close to each other. The dihedral angle is 0 degrees. As a result, this is like least stable. There's constant repulsions. Over here, the hydrogens are far off from each other, beta. They're far off from each other. Okay, the interactions are the least over here. You see, for this hydrogen and this hydrogen, the angle is 180. This hydrogen, 180. This hydrogen, 180. That is why over here the interactions are the least, and that is why they are more stable. Now, this is what Sawhort's projection looks like. It is viewed along the molecular access, okay? And attached to it are the three lines that are inclined at 120 degrees. This is what Sawhort's projection looks like, where this is eclipse. You see hydrogen, hydrogen. Okay, this. this, this. You see their orientation, and over here you look at this 1, 1, opposite, 180 degrees, 2, 2, 3, 3, opposite. Right? So the interaction between them is the least. Now, relative stability of conformations, as I've already told you, staggered conformation bonds are at maximum separation, right? The dihedral angle is the maximum over here. Dihedral angle is what? 180 degrees, maximum. They're at maximum separation. Thus, bonded electrons have minimum repulsion. See, like atoms, if they are close to each other, they'll repel. We are already aware of the fact that like repel, opposites attract. So when like atoms are around, are bonded, are close to each other, they will repel. But in eclipse conformation, bonds are close and repulsions are maximum. Thus, it is less stable. In eclipse conformation, the destabilization is due to the torsional strain. Of all the conformations of ethane, the staggered form has the least torsional strain and the eclipsed form has the maximum torsional strain. Okay, beta, I hope we are clear with this. The relative difference in energy content between eclipse and staggered is 12 kilojoule per mole inverse. This is a small barrier of rotation. To rotation is called torsional barrier. This energy is not large enough to prevent the energy. See, more had been the energy, it would have prevented the rotation. But it is so small that happily it's rotating, At room temperature, both eclipsed and staggered form is obtained, is seen. Thus, the conformers keep on changing from one form to another. The eclipsed conformation is least stable, whereas the staggered conformation is most stable. Now, this is what conformation of N-butane looks like, beta. So, you see over here CH3, CH3. They are at poles apart. This is a staggered. CH3, CH3. But the CH3 is, dihedral angle with CH3 and H is 0. So, this is eclipsed. Okay, now this is not staggered. See, for it to be staggered, the CH3 and the CH3 should be at 180 degrees. If they are at any angle other than the 180 degrees, okay, if they are at any angle, okay, what is Gaussian? If theta should not be equal to 180 degrees, theta should not be equal to 0 degrees. If the torsional angle is not 180 degrees, is not 0 degrees, then in that case it is Gaussian. So this is Gaussian. Then you have fully eclipsed CH3 with CH3, H with H. Okay, here it is eclipsed because CH3 is not with CH3. CH3 is with hydrogen. But here CH3 is with CH3, fully eclipsed. Then again Gaussian, then again eclipsed. Okay, so in this case, what you need to understand is if you have to know about the stability, anti, that is staggered is more stable than Gaussian. Gaussian is more stable than eclipsed and eclipsed is more stable than fully eclipsed. I hope this is clear, beta. Please have a look. I hope this is clear. I hope this is clear, beta. So with this we have come to the end of our session with respect to alkanes. In the next session, we will be learning, that is part 2, we shall be learning about alkenes and alkynes. All right. And in the third part, we shall be learning about benzene. So I shall now be ending the session. All right then, kids, I shall now be ending the session and I shall see you in the next session where we will be discussing about alkenes and alkynes in detail. So until we meet next, keep smiling, keep revising and stay healthy. Bye-bye.